Introduction. Yes, so today I'm going to be presenting some experiments on magnetic reconnection and turbulence in laboratory plasmas, which we produced on the Magpie pulse power generator at Imperial College in London. Now, the interesting thing about these plasmas, and I put this twist on given the title of this seminar series, is that they have some interesting links to the sort of physics that you would find in the convective zone of stars, which is quite a collisional regime. Which is still very interesting and quite difficult to study using remote sensing techniques. I'll be talking a bit more about that later. I'd just like to start by thanking all the people who've been involved in running these experiments, the Magpie team helping set up and get the data, the Cerberus team who provided us with the high power laser, and the Gorgon team who ran the simulations for us. And also particular thanks to Nuno Loureiro and Andrea Ciardi for their help with all of the theoretical understanding. So as a bit of a pictorial summary of what I'm going to be talking about today, I'm going to show you some experiments involving magnetic reconnection, where we observe the formation of the plasmoid instability within a reconnection layer. I'll also show you some experiments trying to create magnetohydrodynamic turbulence using a merging flux tube experiment. I'm going to talk about some new diagnostics we've been developing for studying turbulence in high energy density plasmas. And finally, I'll speak a bit about Puffin, which is a new pulse power facility which I'll be building at MIT next year. So start with, what is magnetic reconnection? Well, it's a ubiquitous process. It happens everywhere in the universe when oppositely directed magnetic fields are brought together within a plasma. As these magnetic fields get closer and closer, they generate an intense sheet of electrical current, which breaks the frozen-in condition of ideal MHD. And this allows the magnetic field lines to be broken and to be reformed to change their topology. Now, at the same time, this intense sheet of electrical current ohmically heats the plasma, converting magnetic energy into thermal energy. And these field lines, which are reformed, are highly stressed and they want to relax. And as they do so, they drag plasma out with them, accelerating it. But this is a mechanism which also converts magnetic energy to kinetic energy. So along with changing the topology of plasmas, magnetic reconnection is also responsible for changing the energy balance within the plasma. Now, this model here is a sort of laminar model that we've had since the 50s, and almost as long we've known that this model isn't particularly good for most of the plasmas we see in the universe around us. To give you an example from the sun, this is a solar flare erupting, and the predicted timescale varies depending on exactly what numbers you use. One source I found claims a predicted timescale of around 1,000 years, but in reality, we know that these events happen on very short timescales, often only tens of minutes. So there's a huge disconnect between the predictions and the reality. So a lot of work has gone into finding new theories of magnetic reconnection, which can explain these very fast reconnection rates. Now, one of those theories is this, the plasmoid instability. This plasmoid instability takes this uniform laminar current sheet and shreds it. It breaks it up into a large number of very intense sheets of electrical current surrounded by O points in the magnetic field. Now, these are the plasmoids. These very intense current sheets very rapidly annihilate the incoming magnetic field, leading to very fast reconnection. And they also cause very strong anomalous heating of the reconnection layer. And in the experiments that I'm going to show you, we create a plasma in which we believe this plasmoid instability occurs. We have flows of plasma coming in from the left and the right-hand sides, and they collide at the midplane, and they carry oppositely directed magnetic fields. They generate a reconnection layer, just like in the image here. But you can see that this reconnection layer is not uniform. In fact, it rapidly breaks up into a chain of bright blobs here. This is optical self-emission, which we believe are the plasmoids predicted by this theory. And I'll be talking a lot more about those later. But for now, as I said, I want to put a bit of a heliophysics spin on this and talk about some different regimes of magnetic reconnection, because a lot of work on magnetic reconnection focuses on this collisionless regime. Now, this collisionless regime is very appropriate to regions of the sun like the solar winds, the corona, and the surface layers, the photosphere and the chromosphere. And here, the mean free path of the plasma is much larger than other length scales, such as the ion skin depth and the electron skin depth. And these conditions have been well studied in many experiments like MRX, TREX, and of course, now on FLARE. But there are other zones inside the sun which are also interesting. And one of these is the convective zone. Now, the convective zone is just a bit down from the photosphere and the chromosphere, but it's surprisingly difficult to study because it's opaque. We can't really use our remote sensing techniques anymore. But what we do know about the convective zone is that it's a highly collisional plasma. This means that the mean free path is now smaller than both the electron and ion skin depths. We can really treat this plasma as a fluid, a magnetohydrodynamic system. And Dmitry Ryutov, in a very interesting paper about 5 years ago, pointed out that this collisional regime here is exactly what you expect in the hot, dense, and highly magnetized or strong magnetic field plasmas that are produced inside the Z-pinches. And so it's Z-pinch based experiments that I'm going to be using to demonstrate reconnection and turbulence for the rest of this talk. So I'm going to start now by presenting data on our reconnection experiments and some of the diagnostics we use to make measurements of all of the relevant plasma parameters within the reconnection layer. And to put this work in context, again, I'm going to talk about other reconnection experiments, which you might be more familiar with. So for many decades now, we've had this magnetically driven type of experiments, such as MRX, T-Rex, and of course, Flare. And here we have magnetic pressures, which are much larger than the thermal and kinetic pressures. That means that the magnetic field dominates the dynamics of this system. And these experiments usually produce long-lasting reconnection layers, and they've been very well diagnosed using techniques such as in situ probes and spectroscopy. Now, in more recent years, there have been a series of laser-driven reconnection experiments. Now, these often work in the opposite regime, in which the plasma beta is very large. The magnetic pressure plays relatively little role in the dynamics, and you have a thin ribbon of magnetic flux, which is transiently annihilated between two expanding laser bubbles. And these experiments have been very well diagnosed using Thompson scattering and proton radiography, amongst other techniques. So in my talk today, I'm going to be presenting pulse power-driven reconnection. Now, these plasmas inherently have beta on the order of unity. That means the kinetic, magnetic, and thermal pressures are roughly the same, and they all play an important role in setting the dynamics of the plasma. And interestingly, this is exactly the beta that you expect in many astrophysical plasmas, which have reached a sort of rough equipartition. And it's also the beta that you expect inside the convective zone of the sun. So this is a very interesting complementary regime of reconnection that we can study. We also make a long-lasting reconnection there by continuously injecting more plasma with more magnetic field into the center here. And these experiments were carried out on the Magpie pulse power generator. Now, Magpie consists of 4 large capacitor banks, which discharge through these 4 horizontal transmission lines. The transmission lines merge at the center here to create a vertical transmission line, which tapers at the top, and it delivers a 1.4 megaampere peak current with a 250 nanosecond rise time into the chamber. Now, this very, very high current and short rise time is equivalent to a terawatt of electrical power inside a volume of around a cubic centimeter. Or to put it another way, it's the entire generating capacity of the US national grid into a volume slightly smaller than the tip of your little finger. And it's that very intense power density which allows us to reach the sort of conditions which we need to study astrophysically relevant plasmas. And if you want a review of some of the excellent work that we've been doing with pulse power on Magpie and on other machines across the world, Sergei Lebedev wrote this paper last year, which I highly recommend. So we use lots of different loads on Magpie to generate different sorts of plasmas, but for the experiments I'm going to be talking about first today, the load is based on this, an exploding wire array. Now, this is a cylindrical cage of thin wires surrounding a thick central conductor. The current passes up through the wires and it returns to ground through the central conductor. And as it does so, it ionizes the surface of the wires. It heats it and creates plasma around it. Now, this plasma takes a fraction of the drive current, and it feels a very large azimuthal magnetic field around the central conductor, which means that the plasma is accelerated radially outward with the J cross B force. Now, as that plasma is accelerated outward, it drags with it a fraction of this driving magnetic field. And so we have this cylindrically diverging source of magnetized plasma, and the plasma is continuously replenished. So as long as there's current flowing through the wires, we continue to eject plasma outwards. To make a magnetic reconnection setup, we place 2 of these exploding wire arrays side by side, and we drive them in parallel. So again, the current flows up through the wires and down through the central conductor. And as it does so, it ablates the plasma off, which drags with it this azimuthal magnetic field. By placing these 2 arrays side by side, it means that when the flows collide at the midplane, the magnetic fields they carry are equal in magnitude and opposite in direction, and so symmetric magnetic reconnection occurs. As I mentioned, the flows are sustained for the drive time of the Magpie generator. This is a very quasi 2-dimensional system. There's very little variation in the inflows in the out of plane direction. And it's also a very collisional system, as I spoke about before. There's very little guide field in this. We don't apply any sort of external guide field. So we don't expect any magnetic fields in the out of plane direction. Now, we've had a number of publications on this work over the years. My colleague Lee Suttle has published several times about experiments he carried out using aluminium wires. With aluminium, we had super alphanic inflows. We saw magnetic flux pile up and the formation of shocks outside the reconnection layer and strong radiative cooling. But in the experiments I'm going to talk about today, I'm going to focus on carbon wires, which gave us flows which were subalphanic and where the radiative cooling was negligible. So we can reach very different regimes by changing wire material. And in terms of experimental data, I want to start by showing you this rather beautiful image, which we took using a digital SLR camera, just an off-the-shelf model, pointed into a vacuum chamber with a long exposure. And you can see, even from this very simple diagnostic, the two wire arrays on the left and the right side. And you can see the wires which are glowing here because they're surrounded by plasma. But even more impressive is this very bright region in the center here. And this is the reconnection layer where the plasmas have collided. So it's a very nice image, but it's somewhat lacking in quantitative details. And so in order to get those sort of details, I'm going to talk you through our diagnostic suite. So again, here are the two exploding wire arrays inside the vacuum chamber of Magpie, which is here. And we pass a series of probing laser beams through from every angle that we can find. And we perform a series of different techniques, such as Thompson scattering, Faraday rotation imaging, and end-on probing, where we look at the optical self-emission and also laser-based diagnostics. Looking at this schematically, our end-on diagnostics look down onto the reconnection layer from above, so onto the plane in which the two or the reconnecting magnetic fields lie. Here we use a two-color, two-time laser interferometry system to make maps of the electron density inside the plasma. We also capture the optical self-emission using our fast framing diagnostic, which allows us to look at the development of the dynamics inside the layer. We use a focused laser beam to perform collective Thompson scattering of the ion feature at multiple spatial locations, which gives us spatially resolved profiles of the flow velocity and the electron and ion temperatures. And finally, we use a side-on probing system, so the magnetic fields point into and out of the page. And here we have a two-channel polarimeter with an inline interferometer. This enables us to make maps of the reconnecting magnetic field. So I'll start by looking end-on, down onto the plane in which the reconnecting magnetic fields lie, using our laser interferometry diagnostic. You can see the locations of the wires I've marked here in red, and the disks which hold these wires, which are silhouetted here. But the main features inside this interferogram consist of light and dark interference fringes. Those come from the constructive and destructive interference between a probing laser beam which passes through the plasma and a reference laser beam which passes around. And we can process these interference fringes to get out a map of the electron density inside the plasma. So the densities here are around 10 to the 18 electrons per cubic centimeter. And you can see at first the outflows are strongly modulated from each of the arrays due to the discrete number of wires. The flows collide at the midplane and they create this elongated reconnection layer which fills the entire field of view. But obviously the most obvious feature inside this is this elliptical region of enhanced density. And we believe this is a plasmoid, and I'll be talking more about these plasmoids later on. But for now, I'll just point out that all I've shown you so far is that the electron density at the midplane is enhanced, but that's not actually a signature of magnetic reconnection. For there to be magnetic reconnection, we need to see a change in the magnetic field. We can measure that using our Faraday rotation imaging diagnostic. Now this diagnostic probes side-on, so the magnetic fields point into and out of the page, and you can see the silhouettes of the two exploding wire arrays on the left and the right-hand side. Now, using our interferometry diagnostic along this line of sight, we can get out measurements of the electron density inside the layer here. But we can also split the laser beam and pass it to a two-channel Faraday rotation imaging system. Now this system measures the angle of rotation of the linear polarization of the probing laser beam. And that angle of rotation alpha is linked to the line integral of the electron density and the component of the magnetic field along the direction of the laser beam, which is coming out of the page in this diagnostic. And so that means this angle of rotation tells us about the reconnecting magnetic field. And what I'm showing here is a map of those rotation angles. You can see on one side, the rotation angles are negative, shown in blue. That corresponds to magnetic fields pointing out of the page. On this side, the rotation angles are positive, coded in red, and that means the magnetic fields point into the page. But in this narrow region in the center, there is no overall polarization. It's almost white, and that means that there's very little magnetic field. And by using this polarization map alongside the electron density, we can get an expression for the line average magnetic field inside the reconnection layer, and that's what's shown here in blue. Now, just to try and get some parameters out of this, we fit it with a simple Hare sheet kind of function, a hyperbolic tangent, and that gives us inflowing magnetic fields of around 3 Tesla, and it means the layer width is about 0.6 millimeters. So all of the interesting reconnection physics is happening within this narrow layer, which is around a millimeter wide. And we can study that in more detail using our Thompson scattering diagnostic. So when we do Thompson scattering, we fire a focused laser beam through the plasma and we collect the scattered light. In our experiment, we collect the scattered light using 2 fiber optic bundles on opposite sides of the vacuum chamber. And what's actually going on inside the plasma here is that the incoming photons from the laser beam are scattered by some mode inside the plasma so that they exit in the outgoing direction. And this process has to conserve both momentum and also energy. So by looking at the spectrum of light coming out in different directions, we can learn something about these modes. And these modes are waves inside the plasma. They're electron plasma waves, they're ion acoustic waves. So their properties strongly depend on things like the density and the temperature and the flow velocity in the plasma. And in our experiments, we look at the ion acoustic waves and we look in the collective scattering regime, which means we actually resolve 2 ion acoustic modes, one of which is traveling along the scattering K vector and one of which is traveling in the opposite direction. So these are the 2 modes here. We can learn an awful lot by studying these 2 modes. So for example, if we look at the overall shift of the modes, we can get an expression for the flow velocity. That's sort of like the Doppler shift of the entire feature. We can look at the separation between the 2 modes, and that gives us a measurement of the effective charge in the plasma times the electron temperature. And then we can look at the width of the modes, and we can get out the ion temperature. Now, in many experiments, the ion temperature can be higher than ZTE. And so that means that, in fact, you don't really distinguish 2 discrete modes. You actually have more of a sort of broad feature that covers both of them. But we can still learn about both the electron and ion temperatures using this technique. And in these experiments, I'm just going to zoom in and show you the collection volumes that we have in our experiment. So each fiber optic bundle consists of 14 evenly spaced fibers. So we collect light from 14 distinct spatial locations. And in this talk, I'm just going to focus on light collected by this bundle, which is sensitive to modes which have momentum in this direction. So that's the inflow direction. So this is the raw spectrogram here, and you can see that we have a series of spectra corresponding to different spatial locations, and each spectra has a different Doppler shift and a Doppler broadening. So this spectra here corresponds to plasma outside the reconnection layer here, plasma which is flowing into the reconnection layer. And here we have a significant Doppler shift, but only small Doppler broadening, which means that we have a cold but fast-moving plasma. In the center of the reconnection layer, this spectra here has very significant Doppler broadening, but very little overall Doppler shift, which means that the plasma is hot and stationary. And we can perform this fitting routine for all of these 14 spatial locations, and we can get out profiles of the flow velocity and the electron and ion temperatures. So we can see that the flow velocity is initially around 50 kilometers per second. And this inflow velocity decreases to 0 on a length scale of around 1 millimeter. Now that initial velocity means that the flows are supersonic, but subalfanic. And over that same 1 millimeter length scale, we see dramatic heating of the electrons and of the ions. The electrons are heated to over 100 electron volts, and the ions are heated to over 600 electron volts. And straight away from this Thompson scattering data, we can show that this dramatic ion heating is not due to the inflow kinetic energy. The inflow kinetic energy per ion is only 150 eV. So even if that was fully thermalized, we still wouldn't be able to get up to these very high ion temperatures of 600 eV. So there has to be some other source of energy. And to look for that source of energy, we construct a power balance. We look at the energy per unit time flowing into the layer and compare it to the energy per unit time flowing out of the layer. And we can do that because we have detailed measurements of the magnetic field, the flow velocity, the electron and ion temperatures, and the electron density. And when we compare the inflow power to the outflow power, we get a good match, which is good for 2 reasons. First of all, it shows us that we haven't neglected any important sources or sinks of energy. And secondly, because as physicists, we like to conserve energy. This is quite an important concept. But now we know that the energy is overall balanced. The remaining question is therefore, what is the energy source that provides this dramatic heating? Well, it has to be the magnetic energy, because that's the largest component in the inflows. So now we know where that energy comes from. Another question then is, how does it get there? What is the actual mechanism which converts this magnetic energy into this thermal and kinetic energy? Well, the trouble is the classical heating mechanisms appear to be way too slow. And we can tell that because we can define an experimental time scale. This is the time it takes for a blob of plasma to go from the center of the reconnection layer and exit out of the top at the characteristic outflow velocity, which we measure with Thompson scattering. And that time scale is around 50 nanoseconds. So any heating mechanism you have has to heat the plasma before it exits the reconnection layer. Well, unfortunately, when you take the Spitzer-Brzezinski formulas for the viscosity and the resistivity, you get out timescales which are much, much longer than this experimental timescale. So these mechanisms are simply too inefficient to provide the very dramatic plasma heating we see. And so we need to look for a source of anomalous heating inside the reconnection layer. And what I'm going to suggest, of course, is that this anomalous heating could be caused by the plasmoids, which I've hinted at several times already. So now I think I need to talk about these plasmoids in more detail and convince you that they're really what we're seeing inside our experiment. So I already showed you this electron density map, which shows this elliptical region of enhanced density here. And in the same experiment, 20 nanoseconds later, we made a second interferometry image. We got a second electron density map, and we could track the motion of this plasmoid. And it moves significantly. It's going around at 130 kilometers per second, which is pretty fast. And that's the same speed that we measure using Thompson scattering for the rest of the outflows. So it's being ejected out of the reconnection layer at the same outflow velocity as the rest of the plasma. Now, of course, when I first saw these, I assumed that they were to do with the modulation from the wire arrays. We've only got a discrete number of wires. The flows coming out from the wires are much denser than the flows between the wires. So I assumed that these sorts of plasmoids could form purely from density perturbations in the inflows. But we no longer think that that's the case. And the reason is you can take two lineouts here. One of the lineouts is close to the exploding wire array, where you can see just by eye that the flows are strongly modulated. The second lineout is just outside the reconnection layer, so it represents the inflow that the reconnection layer actually sees. You can see that indeed, close to the exploding wire array, you have a strongly modulated electron density. But those flows merge together and smooth out. By the time they reach the reconnection layer, they're astonishingly smooth. There's very little information about the discrete nature of the inflows left here. Indeed, there may be some remaining information which could act as a small seed for this perturbation, for this instability. But it doesn't seem likely that this inflow profile could give rise to such dramatic changes of the density that we see inside the reconnection layer. But again, right now I'm talking merely about the density of these objects, and they're magnetic objects, they're plasmoids, they should have a well-defined magnetic field structure, and we should be able to measure that. And that magnetic field structure is quite simple. It's that of an O point, same as a sort of current carrying wire. And so if we can have a stationary probe and allow the plasmoid to pass over the probe, we should be able to measure first magnetic field in one direction, then a null in the magnetic field where it changes sign, and then secondly, magnetic field in the other direction. And this is exactly what we did. We placed the classic B-dot probe inside the plasma, and we have two oppositely wound coils of wire, which we digitize separately. The reason for doing this is because in high energy density experiments, it's very easy to spuriously couple some sort of capacitive component from all of the fast electrons and everything flying around. And if you integrate up this signal without checking that you've actually got a nice signal to start with, you can end up with some rather spurious components. But in this case, you can see that our signals are indeed anti-symmetric because the coils are oppositely wound, so they have opposite sign voltage for a given magnetic field. And so we can take the difference of these two signals, and then we can integrate it up and we can get out the magnetic field profile. Now, at the same time, we had our fast framing camera running. So we can run this movie and you can see the plasmoids highlighted with a white arrow. And this plasmoid moves up and it passes over the probe. And as it does so, this orange bar on the figures on the right moves from left to right, indicating the time at which each image was taken. And you can see we trace out this characteristic O-point profile in the magnetic field. For example, to start with, we have the leading edge of the plasmoid interact with the probe, and we get magnetic fields in one direction. Then we have a null in the magnetic field center. And then finally, we have the opposite sign of the magnetic field at the trailing edge of the plasmoid. So indeed, these plasmoids do have the magnetic field structure predicted by theory. They're not just simply a blob of enhanced density. And that gives us a lot of confidence to compare these results with some of the predictions from the theory. The plasmoid instability theory depends on two key dimensionless parameters. S, which is the Lundquist number, it's a dimensionless measure of the conductivity, and L over di, which is a dimensionless measure of the current sheet length in terms of ion skin depth. Now, the first version of the plasmoid instability theory, which was developed, was in the collisional MHD framework, where only the resistive term in Ohm's law is retained. And that in this framework, we found that plasmoids had to form, or it was found that plasmoids had to form at Lundquist numbers greater than 10,000. And that is quite a limitation for experiments and for simulations, because a very large Lundquist number means you need a very hot, large plasma, or if you're an numerical simulation, you need to have a very fine numerical resolution. And both of those things are difficult to achieve. But fortunately for experimentalists and computationalists, some recent work has shown that if you include two fluid effects, like the Hall effect, inside your Ohm's law, there's a new regime of this instability, the semi-collisional regime. And in this semi-collisional regime, plasmoids can form even at relatively modest Lundquist numbers. And when we calculate the dimensionless parameters for our experiment, we find that our plasma lies directly inside this semi-collisional regime. And that's a very nice place to be, because of course there are theoretical predictions, the growth rate and the number of plasmoids that we would expect. That means when we calculate these theoretical predictions and we get a growth rate around 30 nanoseconds, plasmoid number of around 3, that compares very nicely to what we observe in our 12-frame imaging. Give me a second. So these plasmoids are expected to be one possible path towards fully turbulent reconnection. The idea is that the additional intense current sheets generated between each plasmoid can themselves be unstable for plasmoid instability and break up further, causing a cascade of energy down to very small length scales, which is one of the ways that we think about turbulence. Of course, this process can take a very long time, and it's difficult in an experiment to reach those sorts of timescales because you have to drive the plasma over very long timescales. And so what we decided to do was to try and take a bit of a shortcut towards turbulence in a plasma, magnetized turbulence plasma, by starting with the sort of initial conditions that we expect would quickly lead to turbulence. And we did that using a flux tube merging experiment. And that's what I'll be talking about in the second part here. So for this flux tube merging experiment, I want to motivate it by looking at this simulation of magnetized or magnetohydrodynamic turbulence. And in this simulation, the black lines correspond to magnetic flux surfaces, the shading corresponds to the out-of-plane currents. And what we can see in this little blue box are two merging flux tubes with a current sheet between them. And of course, that looks an awful lot like the experiments I was talking about earlier, where we had two expanding flux tubes driven by these exploding wire arrays and a current sheet in between the two of them. But of course, in the full picture of turbulence, we see there are a large number of merging flux tubes, all with current sheets in between them. And so we kind of have this hierarchy of different objects and structures on lots of different length scales. And of course, because there are magnetic fields involved, this turbulence can be considerably more complicated and richer than the turbulence we see in hydrodynamic content. So for example, we can have anisotropy in our turbulence. The properties of the turbulence look different depending on whether we look parallel or perpendicular to the local magnetic field. This also leads to different power spectras in different directions, and also power spectras which can be modified by things like two fluid effects, kinetic effects, and also maybe by the plasmoid instability disrupting these reconnection layers. And in common with hydrodynamic turbulence, there's also a concept of intermittency. Intermittency refers to structures in the plasma which cause there to be correlations between different parts of the plasma on length scales larger than you'd expect from a simple Gaussian noise model. And the intermittent structures here are, again, these flux tubes and the current sheets. But these are all things we'd like to look for evidence of in the laboratory. And we decided to try and approximate this simulation here with an experiment that merged together 8 flux tubes. And for this, we used an imploding wire array. Now, an imploding wire array is like the exploder, but the plasma goes inwards. The current flows up through the wires and then returns to ground through some return structure far away. That means initially, each of the wires has a plasma with an O point of a magnetic field embedded around it. But around all of the wires, there's a global magnetic field structure. And it's this global magnetic field structure which accelerates the plasma inwards with a J cross B force. And as the plasma goes in, it again drags with it these O points in the magnetic field. So these look a lot like flux tubes. These flux tubes collide on axis and merge together. And what we've done is taken again our fast framing camera to look at the dynamics of this, looking down onto the imploding wire array from above. And if I play the movie now, you can see that the initially teardrop shaped blobs of plasma come in, collide at the center, and they generate this long-lived column of plasma. And the plasma is confined on the axis by a combination of the ram pressure from the jets and the magnetic field that surrounds the column of plasma. Now we can estimate some parameters such as density and temperature, etc., for these sorts of plasmas, and we can get an idea of what the dimensionlessly scaled regime we're in. So as I said before, we're in quite a collisional regime. We have a plasma beta on the order of unity. Now our Reynolds number and our magnetic Reynolds number are high, which means we can expect to have MHD turbulence in this situation, but our Prandtl number is less than 1. And this is quite interesting because this combination of a Prandtl number less than 1 and a beta on the order of unity is again exactly the conditions that we expect in the solar convective zone. So we may be able to study MHD, collisional fluid magnetized turbulence, which is relevant to the convective zone in the sun, using these sorts of experiments. Now, other diagnostics that we've tried on these experiments already include interferometry. With the interferometry, we can see plasmas flows coming in from each of the wires, but in the center, it seems like it's a bit of a mess. And if we zoom in here, we can see that there are regions where we can't see any interference fringes, where the density gradients are so large they deflect the probing laser beam out of our optics. There are also regions where we can trace through the interference fringes. And this sort of hints at cellular structures, which again are evocative of those flux tubes and those current sheets, which we know are the building blocks of MHD turbulence. We also saw these cellular structures looking side-on at the column here. So this is an image taken using a stratigraphy diagnostic. You can see the column of plasma here, which is confined by the incoming flows and also the magnetic field around it. But you can see these caustics, these regions of very intense focusing by the plasma on all sorts of different length scales, which again hints the idea that there are lots of different density scales within this plasma here. But these diagnostics are really rather qualitative. We want to have something quantitative. We want to get some real numbers out. So for the rest of my talk, I'm going to be discussing some new diagnostics that we're developing for studying magnetized or MHD turbulence. And I'm going to start by talking a lot about a new diagnostic we've recently developed called an imaging refractometer. And I'm going to demonstrate it using a very simple experiment. This experiment goes back to our old friends, the exploding wire array. And we've just placed a simple planar obstacle here. So we have a diverging source of magnetized plasma colliding with a wall. And if we look at this side on, schematically, it looks like this. You have the plasma flow coming in, you have the magnetic field pointing out of the page. And when this flow collides with the wall here, you would expect in a fluid model for a reverse shock to form. And in this reverse shock here will slowly propagate back upstream into the flow, supported by thermal pressure and strong magnetic pressure behind the shock. Now, when we studied this using a stratigraphy diagnostic, using an aluminium plasma, we saw pretty much exactly that. We've got this very nice, well-defined shock front, which slowly travels back upstream. But when we changed the aluminium wires for tungsten wires, which is a much heavier element, we saw something completely different. Here, using exactly the same experimental geometry, but merely changing the wire material, the flow collides with the wall and then forms this turbulent mess. What we have here are caustics which have formed due to the density gradients within the plasma. And these caustics are on all the spatial scales which we can resolve, which indicates there are density fluctuations over a very large range of length scales. And so we wanted to try and understand this in more detail, because one of the standard diagnostics for turbulence in the HED community at the moment is to take Fourier transforms of these sorts of stratigraphy images. But these Fourier transforms are inherently limited over the length scales which they can study, usually only around an order of magnitude or so. And we wanted to be able to study very, very small length scales so we can probe more of that power spectrum down towards the dissipation scale. So the diagnostic we've developed is called an imaging refractometer. And it's relatively simple to explain in terms of the optics, but I'm just going to rattle through this quickly and point you to the archive paper if you want to learn more about it. Of course, you can ask me questions. What we do to start with is we place a lens at a distance L from the axis of the plasma. And behind that lens, as you know from your optics work, there is both a Fourier plane and an image plane. The Fourier plane contains the angles at which the rays exit the plasma, and the image plane contains the location at which the rays exit the plasma. What we then do is we have a composite lens, which is different along two orthogonal axes. In one axis, this lens simply images the imaging plane here. So it takes the image plane and it places it on the imaging axis. But in the orthogonal axis, the lens has a different focal length. And now it makes an image of the Fourier plane and places that on the orthogonal axis. So the resulting image has spatial resolution in one direction and angular resolution in the orthogonal direction. And it looks like this. So again, this image here has the same spatial axis as the shadowgraphy. So we can see the flow coming in, we can see it interacting with the wall that's on the far side. But now in the vertical axis, we capture the angle at which rays exit the plasma. So in the inflow region here, the upstream region here, where the plasma flow looks relatively laminar, most of the rays exit the plasma with no large deflection angle. They're mostly centered on zero deflection angle. And that means there aren't very significant density gradients within that region of plasma. But as the plasma goes into this turbulent regime, we see much more significant deflections. These significant deflections correspond to density gradients within the plasma caused by turbulence. What we can do to try and make this more quantitative is to take a line out here. So we can look at the spectrum of deflection angles. And that's what I'm showing here. So this is the spectrum of deflection angles. You can see this spectrum much, much broader than when we do the experiment in the absence of a plasma. So this is effectively the response function of the instrument. And this spectrum here is over 500 times broader than this response function. And so we have a very, very high dynamic range. Now, we need a theory to try and understand exactly how this spectrum of deflections relates to the spectrum of density perturbations in the plasma. The very simple theory is to consider just a single deflection on a single spatial scale. That will give us a deflection angle alpha. So you can imagine if we had a range of spatial scales, we would get a spectrum of deflection angles. But what we want to do is try and link all of the density gradients within the plasma, this total spectrum of deflection angles. One way to think about this is possibly in terms of a random walk. As the laser beam passes through the plasma, it's deflected upwards and downwards by density gradients at random. And so you'd expect that this spectrum would look Gaussian at the exit of the plasma. And that's initially what we thought. But when we tried to fit this with a Gaussian, we found that there was significant kurtosis. There were much longer tails than predicted by a Gaussian model. And this is very interesting because we've done some numerical work now that shows that if we generate a cube of plasma which is purely Gaussian, then we get out a Gaussian spectrum at the end here. But when we generate a plasma which is non-Gaussian, that's intermittent, that has these structures inside it, such as the current sheets, the merging flux tubes, then we get non-Gaussian tails. And so it seems like there's an imprint of the intermittency in the spectrum of deflection angles which we measure. We don't fully understand this yet. We're working very hard on the theory at the moment, but this is a very promising diagnostic to try and go beyond the limitations of existing diagnostic turbulence and try and get a handle on things like the intermittency inside the turbulence as well. And here is the archive link. So if you want to read more about this diagnostic, we put this up on archive last week and we're very excited about it. So other diagnostics that we might work on or that we will be working on include Faraday rotation imaging. So again, looking at this imploding wire array, I'm switching backwards and forwards between experiments, but if you cast your mind back to the imploding wire array where we merged 8 flux tubes, the inflowing plasma has no axial magnetic field, which is what you'd expect from geometry. But when the column of plasma forms at the center, we see some evidence for out-of-plane magnetic field. And so that magnetic field must have been twisted from the in-plane to the out-of-plane direction, which is the sort of thing that we would expect magnetized turbulence to be able to do. So maybe we can learn something about the nature of that turbulence by studying the strength of these magnetic fields and also the spatial scales over which they occur. All the diagnostics I've talked about so far have been line integrated. And when we're studying turbulence, we're often interested in the local property. So one idea that we have is to have multi-point Thompson scattering over a very large number of points, all side by side. And if we capture this spectra simultaneously in the ion feature and the electron feature, we should be able to get out local measurements of the flow velocity, the electron ion temperatures, and the electron density. And we want to see the correlations between those parameters as they fluctuate. Because when we're in a regime where beta is on the order of unity, we would expect that a fluctuation in the velocity should lead to a fluctuation in the density or the temperature as well. So this could be a very powerful technique for trying to understand those correlations. So finally now, I'm going to talk about Puffin, which is a new pulse power facility that I'll be building at MIT next year. And I want to motivate it by looking at some of the experiments that I discussed earlier in this talk. These experiments include the development of the plasmoid instability within the reconnection layer, and also the flux tube merging, which generated this turbulent column of plasma. And in both cases, these instabilities and turbulence took time to develop. And this means that if we want to try and understand these plasmas in a way that's relevant to astrophysical context, we need to be able to drive the plasma over very long timescales, because these astrophysical plasmas also have long timescales to develop. And so what we're looking for is a driver of plasma which can work and sustain the plasma flows over these very long timescales. And this is exactly the idea of Puffin. So Puffin consists of these 8 LTD linear transformer driver stages, and each stage has 2 capacitors. And these discharge into a vacuum cavity, and the current pulse travels down these vacuum transmission lines into a central chamber. Now, Puffin is designed to deliver a 1.5 megaampere peak current with a 1.5 microsecond rise time. And that's quite different from existing pulse power generators like Magpie or Cobra or Maze or other facilities around the world, which are generally optimized to deliver very short, very intense pulses of current. Puffin instead is designed to deliver a very long drive time, which will enable us to sustain these plasmas over the timescales necessary to see the full development of instabilities and turbulence. So I'm going to conclude now by saying that I've shown you some experiments looking at magnetic reconnection and turbulence in a collisional, magnetized, high energy density plasma, which dimensionlessly scales to the solar convective zone. I showed you experiments of subalfanic reconnection, where we saw anomalous heating with the reconnection layer, within the reconnection layer, which we attributed to the plasmoid instability. I also showed you some experiments with magnetized turbulence, where we merged 8 flux tubes to produce a turbulent column of plasma. This plasma column had a Prandtl number less than 1 and a beta on the order of unity, which again is relevant to solar convective. I also talked about new diagnostics to study turbulence in unprecedented detail, in particular the imaging refractometer diagnostic, which I explained at length. And then finally, I talked about Puffin, which is this new long drive pulse power facility, magnetized high energy density plasma, which we'll be building at MIT starting next year. So thank you very much, and I'll take any questions.
Very nice, clapping. Very